Okay, let's continue our discussion with the Mobius transformations. Here we go. Okay, so recap from the last video. So Mobius transformation looks something like this. So it's a fraction of two linear functions with coefficients a, b, c, d, complex number. They're chosen so that ad minus bc is non-zero. That is to ensure that the Mobius transformation is not just a constant function. We learned that Mobius transformation maps extended complex plane to extended complex plane. If in the special case that there's no z in the denominator, so c is equal to 0 and d is just scaled to be 1, then you have a linear function. And that maps complex plane to complex plane conformally. And it sends infinity to infinity in that situation. Okay. In general, Mobius transformation maps circles and lines to circles and lines. If you think of lines as circles of infinite radius or circles that passes through infinity, then you could think of it as Mobius transformation mapping circles to circles. Okay. And last time, with an explicit formula, we showed that if you pick any three points from the extended complex plane, z1, z2, z3, then you can find a unique Mobius transformation that maps those numbers to 0, 1, and infinity, respectively. Okay, so that's what we did last time. I'd like to kind of clean up some of the claims that I made from the last video. So I said that Mobius transformation forms a group. For that to be true, the composition of two Mobius transformation has to give you another Mobius transformation. So we'll show that. And we'll also show that the inverse of Mobius transformation is another Mobius transformation. Okay, so let's take two Mobius transformation f and g and compose them, right? So if we plug in g into the input for f, here's what we get. Just to clean up the expression a bit, I'm going to multiply top and bottom of this fraction by zz plus h, so I don't end up with a fraction instead of a fraction. So if I multiply that to top and bottom, this is the expression I get. It is still pretty messy. We're going to multiply everything out and collect like terms. And here's what we get. So this times z plus a constant over this constant times z over another constant. So plus another constant. So this is in the form of Mobius transformation. We do have to check that this condition AD minus BC is non-zero. So we do have to check that in this new Mobius transformation. It's messy, but it can be done. So if you multiply it out, FOIL everything out, some of these will cancel out. Let's see, so ACEF cancels out, and BDGH also cancels out. So we have 4 terms left. So let me rewrite that together here. If you look, there's 2 terms that has AD in it. So let me factor AD out of those 2 terms. And the other 2 terms has BC in it. So let me factor those out of those 2 terms. And here's what I get. And you can see that this EH minus FG is the negative of FG minus EH. So pull the negative sign out and we could factor out EH minus FG. This is the final expression we have. So what does this say? Well, the 2 composition F and G, they were Mobius transformation to begin with. So these 2 expression is non-zero, which means if you multiply two non-zero numbers, you're going to get non-zero number, which will guarantee that the composition is a Mobius transformation. Okay, let's check that the inverse is also a Mobius transformation. We could do that by setting Z as the output, W as the input, and then solving for W. So if we do that, we get this expression, which is very much in the form of Mobius transformation, except with a couple of letters switched around with the negative signs. If you multiply negative D and negative A, we'll get AD. And B and C is the same as the original function. So we get AD minus BC. So if the original function is Mobius transformation, then this is non-zero. So the inverse is also a Mobius transformation. So this also guarantees that if the inverse exists, then we have one-to-one correspondence. So that's good. Okay, so the next thing I want to do is to extend the result that we claimed last time. We had a formula to map 3 points to 0, 1, and infinity, respectively. So let's take 6 different points. So 2 triplets, so Z1, Z2, Z3, and W1, W2, W3. And we can find, Mobius transformation F1 that maps the first triplet to 0, 1, infinity, and the second triplet to 0, 1, infinity, respectively. And what we could do is that we can compose these two. So F1 will map Z1, Z2, 3 to 0, 1, infinity. And since F2 maps to 0, 1, infinity, the inverse will go from 0, 1, infinity towards W1, W2, W3. So if we compose these two Mobius transformations, we can go from any 3 distinct points from the extended complex plane to any other 3 distinct complex numbers from the extended complex plane. Okay, so that means that we can pick any 3 points to any other 3 points, and we'll get a Mobius transformation that does that. Let's see if we can do this actual computation with an example. Okay, so let's see. Let's say I want to map 0, I, infinity. So I just chose 3 complex numbers from the extended complex plane to -1, 0, and 1. So let's say I want to find a Mobius transformation that does that. Okay, so what we could do is we can find the Mobius transformation that maps the first 3 numbers to 0, 1, infinity, and we could do that by the formula that we derived last time. Here, I'm putting in Z minus infinity in quotes because infinity really isn't a number yet, right? So, but if we take the limit of this guy, so maybe Z minus T, I minus T over Z minus T, and let T go to infinity, then the limit is 1 here. So these cancels out, and we just have Z over I. Okay, so this is my F1, and F2 is going to be the Mobius transformation that maps -1, 0, 1 into 0, 1, infinity. So this is what I want to do. And again, I could use the same formula, and again, -Z minus 1 is over Z minus 1. So that will do the second thing I wanted. I can compute the inverse by flipping A and D and putting negative sign in front, right? And then compose f sub 2 inverse with f sub 1. So if we put f sub 1, which is just z over I, into here, and then just multiply and top on bottom by I think it'll look a little cleaner. This is what we get, z minus I over z plus I, right? Let's just check that this does what we want. So if we plug in 0 into z here, we get negative I over I, which is just negative 1. So that checks out. If we plug in I into here, then the numerator becomes 0. So we just get 0. So that works. If we plug in infinity, infinity over infinity is 1. So this also works as well. So we found the Mobius transformation that does that by using this composition f2 inverse of f1. Okay, so that systematic formula works, but sometimes actually it might be easier to actually compute directly what the Mobius transformation would have to be. So let me show that just in case you prefer the second method. If you get used to it, it is a faster method. But if you like the first method, that's also okay. So I want you to be able to compute these Mobius transformation that sends 3 points to any other 3 points. Okay, so how can we do that? So we have AZ plus B over CZ plus D. Remember, one of these coefficients could be just scaled to whatever we want. So you can just choose A to be 1 if you want it and do the computation. So that's where I'm going to start. And then look at this carefully. So if I has to map to 0, that means when I plug in I into the numerator, that should cancel out to be 0. So the only way it could map to 0 is if the numerator is equal to 0. So that condition requires you to choose your B as negative I. So we figured out what B would have to be. Okay, another thing we can look at is infinity. So as Z moves towards infinity in this expression, if you take the limit, we're going to get the limit 1 over C, okay? And we want the limit to be equal to 1. So if 1 over C is equal to 1, then C would have to be equal to 1. Okay. And then we only have one constant left, right? So we chose A to be 1, B was negative I, C was equal to 1. So plug all that in and plug in D and plug in the last thing we have to plug in is plug in 0 and get negative 1. So we got 0 minus I divided by 0 plus D. And we want that to equal to negative 1. So negative I is equal to negative D, or D would have to be equal to I. So putting all that together, we get Z minus I is divided by Z plus I, which is the same as the Mobius transformation we got from before, right? And that was a lot faster, but it took a little bit of like looking at infinity, what maps to 0 and what goes to infinity. So it might take a little bit of getting used to. But if you can do that, it's a faster method for finding the Mobius transformation. Okay. So I guess this gives you a way of mapping. So knowing that every circle is determined by 3 points on a plane. And knowing that Mobius transformation maps circles to circles, this allows you to be able to map any circle to any other circle in the extended complex plane. If the 3 points are collinear, then it becomes a line. So you can map any circle to any other circle, and that determines the Mobius transformation. Okay. All right. So we understood Mobius transformation in special cases. If you just look at the coefficient A, the modulus of A tells you the dilation, and the argument will give you rotation of this Mobius transformation. If we only look at the B term of the Mobius transformation, then we get the translation. So this could move the number Z to up, down, left, right, depending on what value B is. And we also understood, I guess, the simplest case of where we have Z in the denominator, and this was called the inversion. It turns out that if you understand these three, then you understand every Mobius transformation, because it's a combination of these three actions, right? So for example, if we're looking at AZ plus B over Z plus D, so in this case, I'm rescaling so that the coefficient C becomes equal to 1, just for simplicity's sake. Then you can rewrite, if you divide AZ plus B by Z plus D, we can rewrite it as A plus this fraction, B minus AD over Z plus D. So we could get this Mobius transformation by first doing a translation, so adding a D, then looking at the inversion, and then by multiplying by constant B minus AD, and then again, finally adding A, so another translation after that. So translate, invert, dilation and rotation with a translation at the end again, and then this is equivalent to the original AZ plus B over Z plus D. Okay. So if you geometrically understand those three things, you technically understand all of Mobius transformation. Okay. So that's it for this video. Okay, I'll see you in a different video. Bye.